Light weighs nothing, zero mass. By the rule you learned in school, momentum needs mass, so a beam of light should push nothing at all. Yet sunlight steers real spacecraft between the planets. It spins metal vanes sealed inside glass. It even helps hold our sun up against its own crushing gravity. So how can something with no mass shove anything? Today we chase that answer. We visit a box that grows heavier when you fill it with a glow. A beam of light that freezes atoms almost to a stop. Living cells lifted and moved by a simple beam of light, and a laser strong enough to fling a tiny ship toward another star. If riddles like these keep you curious, take a second to like and subscribe. The push of light is real and far stranger than it sounds. Let us begin. Picture a bowling ball rolling down a wooden lane toward the pins. That ball carries a push. Scientists call it momentum, and it is the thing that sends the pins flying. Back in school you learned the simple recipe for it. You take how heavy something is, and you multiply it by how fast it moves. Heavy and fast makes a huge push. Light and slow makes a tiny one. A speeding truck flattens a fence. A rolling marble barely taps your shoe. So the rule feels obvious. More weight, more push. Less weight, less push. Now walk that idea all the way down to nothing. What if the weight is zero? By the recipe, the answer falls out fast. Zero multiplied by any speed is still zero. So a thing with no weight should carry no push at all. It should be a ghost. It should slip through the world and never move a single grain of sand. It could scream past you at any speed, and you would feel nothing. That is the rule almost every student is taught. It works for baseballs, for cars, for planets. People have checked it 1 billion times, and for ordinary objects it holds up perfectly. Here is where the trouble starts. Light has no weight. A beam of sunlight weighs exactly zero. Put a ray of light on the most sensitive scale ever built, and it reads nothing. By the schoolyard rule, light should be the ultimate ghost. It should be unable to push, to shove, to move anything. Yet you can already feel the crack forming in the rule. Because light does push. It pushes on metal. It pushes on mirrors. It pushes on spacecraft flying between the planets right now. Engineers build real machines that ride on that push, the way a sailboat rides on wind. The lightest thing in the universe is doing a job that, by the rule, nothing weightless should be able to do. Think about how odd that is. You have a recipe that has never failed for solid stuff. Then the thing with no weight at all walks up and breaks it. Two things you were told cannot both be true. Either the push comes from somewhere the recipe never mentions, or the recipe was only ever half the story. It turns out the recipe was half the story. The simple version, weight times speed, is a shortcut. It works great for slow, heavy things like bowling balls. It quietly falls apart for the fastest thing there is. Nature has a fuller rule hiding underneath, and that fuller rule lets a weightless beam carry a very real shove. Scientists are certain of this. The push of light has been measured in labs, felt by instruments, and used to fly missions across the solar system. This is settled, tested, and confirmed. So one question is left standing. How? To answer it, we throw out the kid version of momentum and hunt for the grown-up one. We find why a thing can carry a punch while weighing nothing at all. But first, a smaller puzzle. If light really pushes, why did nobody notice for thousands of years? Why did fire and sunlight and lamps sit in front of every human who ever lived, without one of them feeling the shove? The answer is that the push of light is almost unbelievably gentle, so faint that it took some of the sharpest minds alive just to prove it was there at all. Hold your hand out in the sunlight for a moment. Warmth? Yes. Brightness? Yes. A push? You feel nothing. And that is the whole problem. The shove of light is real, but it's so tiny that your skin can never sense it. How tiny? Let me give you a picture you can hold on to. Take an entire football field, end zone to end zone. Now imagine full noon sunlight pouring straight down onto every blade of grass on it. Add up the total push of all that light across the whole field. The answer sounds like a joke. It comes to about the weight of a single nickel resting in your palm. One coin. Across a field big enough for a stadium of fans. So of course nobody noticed. The push of sunlight on a person is smaller than the weight of an eyelash. It is drowned out by every breeze, every heartbeat, every twitch of the air. For all of human history, it hid under noise 1,000 times louder than itself. This is why the schoolyard rule survived so long without a scratch. In daily life, the push of light might as well be zero. You will never feel it move a cup, tip a pencil, or ruffle a page. But go somewhere with no air, no gravity pulling hard, no friction dragging things down. Go to open space. Out there, that whisper of a push has nothing to fight against. And a whisper that never stops, that presses hour after hour, day after day, quietly adds up into something that can steer a spacecraft across millions of miles. So the crack in the rule was there the whole time. The trouble was simply seeing it. For centuries, the light pushing on tables and walls and human faces was far too weak to catch. People needed a stage where the effect was blown up huge, a place where light was slamming into something for millions of miles, where the push had room to reveal itself. And here is the strange gift of history. Long before anyone had a lab, before anyone had the word momentum, nature built exactly that stage and hung it in the night sky for everyone to see. You have almost certainly seen a photo of it. A bright ball of ice trailing a long glowing streak behind it as it swings past the sun. A comet. For thousands of years, people watched comets and felt fear. They thought the streaks were omens, warnings, signs of doom. What they were staring at, without knowing it, was the push of light drawn across the sky in glowing dust. The comet's tail was the first proof, sitting in plain sight, that light can shove matter around. But nobody read the clue correctly. To everyone watching, the tail seemed to just stream out behind the comet, the way smoke trails a moving car. Simple, boring, expected. Then one careful man did something almost no one ever does. He stopped assuming, and he actually looked at which way the tail pointed. What he found broke his mind a little. The tail was ignoring the comet's motion completely. It was pointing somewhere else, obeying a master the comet could not see. That man lived 400 years ago. He had no telescope worth the name, no physics, no idea what light even was. And still he guessed the truth. The year is 1619, and a German astronomer is staring at a comet, deeply confused. His name is Johannes Kepler. You may know him as the man who worked out how the planets loop around the sun. Right now, though, he is stuck on something small and stubborn. A comet's tail. It is behaving in a way that makes no sense to him. Here is what should happen by common sense. A comet flies through space like a runner sprinting down a track. Its tail should trail behind it, streaming back the way it came, like a scarf flapping behind a bike. Motion in front, tail behind, easy. That is what everyone assumed for ages, and it is wrong. Kepler tracked the tail carefully, and he caught the comet doing something impossible. As the comet raced in toward the sun, its tail did trail behind. But then the comet whipped around the sun and started racing back out. And the tail swung all the way around and now pointed forward, ahead of the comet's own motion. Stop and picture that. A runner sprinting with their scarf streaming out in front of their face into the wind. It should never happen. Yet the comet did it every single time. The tail was not following the comet at all. It was obeying the sun. No matter where the comet flew, its tail always aimed straight away from the sun, like a weather vane locked onto one fixed point. Coming or going, the sun was always at its back. Kepler made a wild leap. Something was streaming out of the sun, he decided, and physically blowing the comet's tail away, like wind bending a candle flame. A pressure, a push, pouring out of the sun in every direction and shoving the comet's dust outward. Remember, this man had nothing. No idea what light was made of. No physics of energy or momentum. He was 400 years too early to prove a word of it. And still, staring at a smear of light in the dark, he reached out and touched the right answer with his fingertips. He was partly right, and we should be honest about which part. We now know two different things stream off the sun and stretch a comet's tails. One is a wind of tiny particles. The other, the one that shapes the bright dusty tail, is exactly what Kepler guessed. The pressure of sunlight itself, pushing the dust outward grain by grain. So the comet's dust tail is the oldest evidence we have, written across the sky, that light carries a real push. Kepler saw the clue centuries before anyone could explain it. But a guess is not proof. Kepler could point at the sky and say, light must be pushing that. He could not measure it. He could not show why. For all his brilliance, he was describing a magic trick without knowing how it worked. The how would wait more than 200 years. It would come from a quiet Scottish man scribbling equations, someone who never set out to study comets at all. He was chasing something that felt totally separate. The link between electricity and magnetism, the crackle in a wire and the pull of a compass needle. He had no plan to explain the push of light. But buried inside his equations, without his even looking for it, a shocking prediction was waiting. In the 1860s, a Scottish physicist is filling page after page with equations, chasing electricity and magnetism. His name is James Clerk Maxwell, and he is trying to answer a simple-sounding question. What is the deep connection between a spark, a magnet, and a compass? He is not thinking about comets. He is not thinking about the push of light. He just wants to write down the rules that tie these forces together. Maxwell manages it. He boils all of electricity and magnetism down to a tidy set of equations. Then he does something with them that changes everything. He asks what they predict. The equations answer back with a wave, a ripple made of electricity and magnetism, taking turns, feeding each other, rolling forward through empty space. And when Maxwell works out how fast this wave must travel, he gets a number he already knows by heart. The speed of light. The shock lands like a hammer. Light is not some separate mystery. Light is this wave. Light is electricity and magnetism, dancing together and flying across the room. In one stroke, Maxwell had explained what light actually is. That alone would make him famous forever. But his equations were still talking, and they had one more thing to say. Maxwell looked closer at his light wave and realized it must carry momentum. It must push. When his wave of electricity and magnetism hits a surface, the math demands that it press on that surface, like a hand laid flat against a wall. Light, his equations insisted, shoves whatever it lands on. For the first time in history, someone could explain Kepler's comet. The reason a tail points away from the sun was written right there in the equations. Sunlight is a wave carrying momentum, and it presses the comet's dust outward. Maxwell even worked out how hard light pushes, and the answer matched the mystery perfectly. It was ferociously weak. His math said the push of light was so faint that catching it in a lab would be a nightmare. Here is a way to feel how gentle it is. Imagine the sunlight landing on your entire body on a bright day. The total push from all of it is smaller than the weight of a mosquito standing on your shoulder. That is the shove Maxwell was asking people to detect. So he had done something remarkable and something frustrating in the same breath. He had proven, with cold math, that light carries a push, and he had shown that the push was almost too tiny to ever measure. This is the part worth sitting with. Maxwell was certain. Not guessing like Kepler, but sure because the numbers left no room to wiggle. The push of light was real. He just handed the hard job to someone else. Somebody would have to build a machine delicate enough to feel a mosquito's whisper. But there is a deeper puzzle hiding under all of this, and Maxwell's wave alone cannot crack it. His equations described light as a wave, a smooth ripple with no weight and no solid stuff. So how exactly can a weightless ripple carry a punch? Where does the push come from when there is nothing there to weigh? To answer that, we need a young clerk in a patent office, a man about to rewrite the meaning of energy, mass, and motion. His name was Albert Einstein, and he hid the real answer inside one line that most people have never seen. You already know one equation from Einstein, even if you know nothing else about physics. Energy equals mass times the speed of light, squared. Those famous letters sitting on 100 posters and t-shirts. Most people think that little line is the whole story. It is only a corner of it. The full rule is longer, and it is the one that finally explains the push of light. Almost nobody outside a classroom ever sees it. So let me walk you through it in plain words, with no scary symbols. Einstein figured out that a thing's total energy comes from two separate sources added together. Think of it like the total loudness of a song coming from two speakers. The first speaker is mass. This is the energy locked inside just by existing, by being made of solid stuff. A rock sitting still on a table has this energy, quietly, doing nothing. This is the part the famous equation describes. The second speaker is motion. This is the energy of moving, the momentum the push a thing carries because it is travelling somewhere. A thrown rock has this on top of the first kind. Einstein's Fuller rule says you combine these two to get a thing's total energy. and he combined them in a specific way. He did not simply stack them like blocks. He joined them the way the two short sides of a right triangle join to give the long slanted side. Hold that triangle in your head, because it is the key to everything. Picture a right triangle, the kind with one square corner. One short side is the mass energy, the other short side is the motion energy, the momentum, and the long slanted side, the hypotenuse, is the total energy of the thing. For an ordinary object, both short sides have length. A rolling ball has some mass and some motion, so both sides are there, and together they set the total. This triangle is the grown-up version of the momentum we promised you back at the start. The schoolyard recipe only ever looked at part of it. Einstein's triangle looks at the whole thing, and it works even at the speed of light, where the old recipe shatters. Scientists have tested this triangle to absurd precision. Inside giant machines, they slam particles together near light speed and watch the energy and momentum come out. Every single time they add up exactly the way the triangle demands. This is not a guess or a pretty idea. It is measured, hard, and confirmed, over and over. Now here is where it gets beautiful, and where the whole mystery starts to dissolve. We have been asking how a weightless thing can carry a push. In triangle language, we are asking something sharp and simple. What happens to the triangle when one of its sides, the mass side, shrinks to nothing? For a rock, the mass side is long. For a person, longer. But light has no mass at all. So for light, that mass side is not just short, it vanishes completely. Its length drops to 0. A triangle with one side gone. Think about what that even looks like. What is left when you erase the mass? The answer that falls out is so clean, so simple, that when you see it, the entire riddle of the pushing light collapses in a single step. Take Einstein's triangle and do something almost cruel to it. Erase the mass side. For light, remember, there is no mass. So that short side of the triangle, the one built from mass energy, has a length of 0. Watch what happens to the shape when a side disappears. If one short side has no length, the triangle flattens. The long slanted side and the remaining short side fall right on top of each other. They become the same length. There is no gap left between them. Turn that back into plain words and you get something stunning. For light, the total energy and the motion energy are simply equal. The push side and the total side are one and the same. Say it straight. For anything with no mass, energy equals momentum times the speed of light. That is the whole secret, written in one short line. Look at what that line is telling you. If a massless thing has any energy at all, it is forced to have momentum. The two come welded together. You cannot hand light some energy and hold back the push. The push is the energy. There is no separating them. This is the moment the mystery breaks open. We started with a rule that said no mass means no push. That rule came from the kid version of momentum, weight times speed. But we now have the grown-up version, and it says the exact opposite for light. No mass does not mean no push. For a massless thing, the push is guaranteed, locked to its energy by an iron law. Sunlight carries energy. You feel that energy as warmth on your face, and because sunlight has no mass, that energy has no choice. It must come bundled with momentum. Warmth and push, arriving together, two faces of the same thing, so the ghost was never a ghost. The schoolyard rule told us a weightless thing should drift through the world touching nothing. The real rule says a weightless thing with energy is basically made of push. Let me give you a way to feel how tight this bond is. For light, energy and momentum are like the two sides of a coin. You cannot have one side of a coin without the other. You cannot spend the heads and keep the tails. Energy and momentum in light are stuck together just like that, back to back, impossible to pull apart. And this is not a special trick that only sunlight can do. Every massless thing must obey it. Radio waves, X-rays, the glow of a phone screen, the light from a distant star. All of them carry energy, so all of them carry a push. Every beam of light that has ever touched you gave you a tiny, unfeelable shove. Scientists are fully certain of this equation. It has been checked in labs across the world and never once failed. This is settled ground. But notice what this new rule quietly forces on light. If a massless thing must always carry momentum whenever it has energy, then it can never truly sit still. A resting thing has no motion energy, no push. Yet light is never allowed to have 0 push, so light is never allowed to rest. which raises a strange and specific question. If light can never stop, never slow to nothing, then how fast is it forced to go, and why that speed and no other? The answer is that a massless thing has only one speed it is ever allowed to move, and it can never, ever change it. Before we chase the speed of light, we need to answer a smaller question hiding inside everything we just said. We keep talking about a bit of light carrying energy. But how much energy? What decides whether one flash of light is packed with punch or nearly empty? The answer turns out to be something you see with your own eyes every day: colour. Scientists learned to think of light as coming in tiny packets. Each packet is a single grain of light, the smallest piece there is. We call one of these grains a photon. When you turn on a lamp, trillions upon trillions of photons pour out and flood the room. Now here is the part that feels almost too simple. The energy inside one photon is set entirely by its colour. Picture the colours of a rainbow, red on one end, violet on the other. As you slide from red toward violet, the light is vibrating faster and faster, shaking more times each second. Red light shakes slowly, blue and violet light shake quickly. That rate of shaking is what your eye reads as colour. And the faster a photon shakes, the more energy it carries. Red photons are the gentle ones, low energy, slow shakers. Blue and violet photons are the fierce ones, high energy, fast shakers. Same light, wildly different punch. And the only thing that changed was the colour. This is why a sunburn comes from the light you cannot even see. Beyond violet sits ultraviolet light, shaking faster still, each photon carrying so much energy it can tear into the cells of your skin. Meanwhile, the warm red glow of a sunset shakes slowly and passes through you, doing almost nothing. Same sun, different photons. One burns, one soothes. Keep sliding past violet and the photons only get more savage. Push far enough and you reach X-rays, photons shaking so fast and packing so much energy, they punch clean through your body. That is exactly why a doctor uses them to photograph your bones. Each X-ray photon is a colour your eye cannot see, carrying a wallop that ordinary light never could. Go the other way, past red, and the photons grow gentler. You reach the infrared glow of a warm brick, then radio waves, the calmest photons of all, shaking so slowly they slip through walls without stirring a thing. So a photon's energy is really just its colour, dressed up. Say a colour and you have named its energy. This is measured, exact, and rock solid. Physicists lean on it every single day. Now connect this to what we found a moment ago. We proved that for anything massless, the push and the energy are welded together, and a photon has no mass. So a photon's push must be welded to its energy too, which means it is welded to its colour. Feel where this is going. A blue photon carries more energy than a red one, so a blue photon must also carry a bigger push than a red one. The colour of light quietly decides how hard that light can shove. We now have two clean facts sitting side by side. A photon's energy comes straight from its colour, and a photon's push comes straight from its energy. Snap those two facts together, and out pops a single tidy formula for the momentum of light itself. Let us build it right now and see exactly how much punch is hiding inside one grain of light. Let us put the whole answer together in one place, like clicking the last two pieces of a puzzle into a picture. Piece 1 from a moment ago. For anything with no mass, energy equals momentum times the speed of light. That was the clean line that fell out of Einstein's flattened triangle. Piece 2. A photon has no mass, so it obeys that line perfectly. Flip the line around, and it tells you the photon's momentum directly. A photon's push equals its energy, divided by the speed of light. That is it. That is the full answer to the question we started with. The momentum of a grain of light is simply its energy shared out over the speed of light. No mass appears anywhere in that sentence. None is needed. The push was never coming from weight. It was coming from energy the whole time. Read the formula slowly and it starts telling you things. More energy in the photon means more push. So the fierce blue and violet photons, the fast shakers, shove harder than the gentle red ones. The colour of light really does set its punch, exactly as we guessed. And the speed of light sits on the bottom of the formula, dividing. That speed is a colossal number, about 186,000 miles every second. Dividing by something that gigantic crushes the answer down to almost nothing. This is the deep reason the push of light is so absurdly weak. The energy of a photon is real, but you split it across one of the largest numbers in all of nature, and what survives is a whisper. Let me make that whisper concrete. To feel a push equal to the weight of a single apple resting in your hand, you would need to be struck by light so intense it would blind and burn you instantly. A beam brighter than staring into a welding torch from an inch away. That is how gentle one grain of light truly is. So why does light steer spacecraft then? Because space hands light two gifts. First, endless numbers. The sun throws out an unimaginable flood of photons, far more than any counting could reach, every second without pause. Second, endless time and no friction. Out in the emptiness, nothing pushes back. Each tiny shove simply adds to the last, hour after hour, month after month. Picture one snowflake landing on your arm. You feel nothing. Now picture snowflakes landing without stopping, gently, for a year, in a place where none of them ever melt or blow away. The pile would bury a house. Sunlight in space works the same way. Each photon is a snowflake of push. Given enough of them and enough patience, they move ships, so we have cracked the core riddle completely. A photon carries a push because it carries energy, and for anything massless, energy and push are the same thing wearing two hats. Mass never enters the story. The schoolyard rule failed because it only knew about mass. Nature's real rule runs on energy. Scientists trust this formula down to the tiniest measurement. It is not a maybe. It is one of the most tested relationships in all of physics. But this answer drags a strange new law in behind it. If a photon's push is locked to its energy, and it can never carry zero push, then light can never stand still, and that forces a bizarre rule onto every massless thing in the universe. There is exactly one speed it is allowed to move, and it can never change it, no matter what. Try to imagine light sitting still, just for a second. A beam of sunlight frozen in the air in front of you, hanging motionless like a bug in glass. You cannot do it. And it is not a failure of imagination. Nature itself cannot do it. Light frozen in place is a thing that has never existed and never can. Here is why, and it comes straight from what we just found. A resting object has no motion, so it has no push. Its momentum is zero. But we proved that a photon's push is welded to its energy, and a photon always has energy. So a photon can never have zero push, which means a photon can never be at rest. Ever. So light is trapped. It is forbidden from stopping. The instant a photon exists, it is already moving at full speed, and it stays there until the moment it is swallowed by something and ceases to exist. There is no slowing down. There is no coasting to a stop. There is no in-between, and it goes further. A massless thing is not only forbidden from stopping, it is forbidden from going any speed except one. It cannot dawdle at half speed. It cannot creep. The math allows a massless thing exactly one speed and nothing else. That speed is the speed of light. Let me give you a feel for how fast that one allowed speed is. In a single second, light could lap the entire Earth about 7 times. Blink, and in that blink a photon could cross the United States coast to coast more than 30 times over. That is the only pace light is ever permitted to keep. So the speed of light is not really a speed limit for light at all. It is light's one and only setting. Massless things are born at that speed, live their whole lives at that speed, and die at that speed. They know no other way to move. There is a way to make peace with how strange this is. Think of mass as a kind of anchor. Anything with mass drags an anchor around, and that anchor is what lets it slow down, stop, and rest. It also weighs the thing down, keeping it from ever reaching top speed. A photon has no mass, so it carries no anchor at all. With nothing to weigh it down, and nothing to stop it, it simply flies at the one speed nature allows, forever, without effort. This is fully confirmed, checked in countless experiments. Every massless thing we know of moves at exactly this speed, and none of them can be caught sitting still. And that anchor idea is about to pay off in a huge way because it swings both directions. We just saw the light side of the coin. A massless thing has no anchor, so it must fly at the top speed and can never slow down. So what about everything else? What about you, a bus, a bullet, a planet? anything that does have mass and does carry that anchor. The rule flips completely. If having no anchor forces light to always fly at top speed, then having an anchor should do the reverse. It should forbid you from ever reaching that speed at all. And it does. There is a hard wall in the universe, a speed no massive thing can ever touch, no matter how hard it is pushed. Try to cross it, and something almost frightening happens to you. Imagine flooring the gas pedal in a car that never runs out of fuel and never breaks down. Faster and faster, day after day, the needle climbing. Sooner or later you think you would blow right past the speed of light. Common sense says a big enough engine, given enough time, can reach any speed at all. Common sense is dead wrong. You could push forever and never get there. The speed of a light is a wall for you, and it is a wall you can never break no matter how monstrous your engine. Here is the reason, and it is one of the strangest facts in all of science. As you speed up, you get harder to speed up. The faster you go, the more the universe resists shoving you faster still. Your anchor, the one that comes with having mass, grows heavier the closer you creep to light speed. Near the very edge, this resistance goes berserk. To nudge you just a hair faster, the universe demands a colossal shove. A hair faster than that, and it demands more still. The closer you crawl toward light speed, the more the required push balloons, climbing without any ceiling at all. To actually reach the speed of light, you would need an infinite push. Not a huge one, not an unimaginable one, an endless, never finishing, impossible one. And nothing in the universe can supply an infinite push. So you are stopped cold, a sliver short of the wall, forever. This is the flip side of the coin from the last chapter, and now both sides fit together perfectly. Anything with no mass carries no anchor, so it must fly at the speed of a light and can never slow down. Anything with mass carries an anchor, so it can never reach the speed of light and can never speed all the way up. Massless things live at that speed. Massive things are locked out of it. The line between those two fates is mass itself. Let me make the resistance vivid. Imagine pushing a shopping cart. Empty, it rolls with a finger. Now imagine the cart getting heavier the faster you push it. A jog, and it feels loaded with bricks. A sprint, and it feels like dragging a truck. Full speed, and it feels like shoving a mountain that grows taller the harder you lean. That is what approaching light speed feels like to the universe. The push you need runs away from you. This is measured every day, not just imagined. In the giant machines where scientists race particles, they watch this happen in real time. They pour more and more energy into a particle, and it refuses to cross the wall. It just creeps closer and closer to light speed, never touching it, its resistance climbing exactly as the math predicted. Confirmed, again and again. So now the whole picture snaps into focus. Mass is the great divider of the universe. On one side, the massless things, forced to fly at light speed forever. On the other side, everything with mass, forbidden from ever reaching it. And a photon with its zero mass sits proudly on the far side, carrying its push at the one speed nothing else can match. For a long time, all of this lived only in the minds of theorists. Beautiful math on paper. Kepler had guessed, Maxwell had calculated, Einstein had explained, but nobody had ever actually caught the push of light in a real experiment and measured it with their hands. That changes now in a cold Russian laboratory, where one stubborn man is about to weigh a beam of light. Around the year 1900, in a Moscow laboratory, a physicist is trying to do something everyone calls impossible. His name is Pyotr Lebedev, and he wants to measure the push of light. Not guess it, like Kepler. Not calculate it, like Maxwell. Actually feel it move a real object, in a real room, and put a number on it. For 40 years since Maxwell, no one had managed. The push was simply too faint to catch. Remember the size of the thing he is hunting. The shove of a beam of light is lighter than the weight of a dust speck. Any breath of air, any tremor in the floor, any flicker of heat would crush the signal completely. Trying to weigh light is like trying to hear a single whisper in the middle of a roaring stadium. So Lebedev became an artist of removing noise. He built a tiny set of thin metal wings and hung them from a thread so fine it was almost invisible, inside a sealed glass chamber. The idea was simple and daring. Shine a light on the little wings. If light truly pushes, the wings should turn, twisting the thread by a hair, then measure that twist. But the tiniest amount of air ruined everything. Warm light hitting the wings would heat the air around them, and the moving air would kick the wings far harder than the light ever could, drowning the real signal. So Lebedev fought to suck the air out, chasing a vacuum cleaner than almost anyone had made before until barely a wisp of air remained inside his chamber. Then he sat in the quiet and shined his light. The wings moved, just a hair, a twist so small he needed a beam of reflected light and a careful scale just to see it. But it moved, and it moved the right way, and it moved by the right amount. The push he measured matched Maxwell's prediction almost exactly. Sit with what that means. For the first time in human history, a person had reached out and caught the push of light in their hands. The thing Kepler saw in a comet and Maxwell buried in the equations was now a real, measured force twisting a real thread in a real room. The ghost had left a footprint at last. It is hard to overstate how delicate this was. Lebedev was measuring a push thousands of times weaker than the weight of a mosquito's wing, and pulling it out from under mountains of noise with tools from over a century ago. People who study the history of physics still shake their heads at how good his hands and patience must have been. This was the turning point. Before Lebedev, the push of light was a beautiful idea. After Lebedev, it was a measured fact of nature. Confirmed, weighed, done. But a single experiment in a single lab is never quite enough for science. One measurement could hide a hidden mistake, a quirk of one man's apparatus, a lucky accident. Before the world would fully believe that light pushes, someone else, somewhere else, with different equipment, had to catch the same faint shove and read the same number. That confirmation was already brewing, an ocean away, in a small American college. Two men there were building their own trap for the push of light, with no idea whether they would catch anything at all. At the same time, in a small American college, two scientists are chasing the very same ghost. Their names are Ernest Nichols and Gordon Hull, working at Dartmouth in New Hampshire. Word of the push of light is spreading, and they want to catch it too on their own bench, with their own hands, to see if the numbers truly hold up. Science lives or dies on this. One lab finding something strange is a headline. Two separate labs, far apart, finding the exact same strange thing, with different tools, is how a discovery becomes trusted for good. Nichols and Hull were about to give the push of light that second proof. They built their own delicate machine, close in spirit to Lebedev's. A pair of tiny surfaces hung from a fine thread inside a chamber, ready to twist if light truly shoved them. Then they fought the same brutal war against noise. The same enemy waited for them. Stray heat, stray air, the faintest tremor, any of it able to swamp the whisper they were hunting. They were meticulous. They measured and remeasured, and hunted down every source of trickery they could think of. They cooled things, they steadied things, they checked their work against Maxwell's math again and again, and the light pushed. Their little surfaces turned, twisting the thread, by an amount that matched the prediction. Two labs, one in Russia and one in America working apart, had now caught the same feather touch of light and read the same answer off their instruments. That agreement is what mattered. When two strangers on opposite sides of the world using their own gear catch the identical faint effect, the odds of a shared mistake collapse toward nothing. The push of light stopped being one person's claim and became a fact the whole world could stand on. Here is a way to grasp the size of what they measured. The push they detected on their little targets was so slight that it would take that same beam pressing steadily for many, many years just to nudge a single grain of sand across a tabletop. And still, with tools from over 100 years ago, they caught it clean and put a number on it. So by the early 1900s, the story looked finished. Kepler had seen it. Maxwell had explained it. Lebedev had measured it. Nichols and Hull had confirmed it. Light pushes and the amount matches the theory perfectly. Case closed. Except science is littered with traps, and one was waiting right in the middle of this triumph. Around this same time, a little glass toy was spinning on windowsills and in shop displays all over the world. A tiny set of black and white paddles sealed in a glass bulb that whirled around whenever sunlight hit them. People pointed at it and grinned. There, they said. Look, you can see light pushing with your own eyes. The toy proves it. They were absolutely wrong. That spinning toy is one of the most famous traps in all of physics. It looks like it shows the push of light. It does the opposite, and the truth of why it spins fooled brilliant scientists for years. Sitting on a sunny windowsill is a little glass bulb with 4 tiny paddles inside, spinning merrily whenever the light hits it. You have almost certainly seen one. It looks like a miniature carousel sealed in glass. Each paddle is black on one side and shiny on the other, and the whole set whirls around a needle. Step into the sunlight, and it spins. Step into shade, and it stops. The toy is called a radiometer, and for a long time it was the perfect trap. Because here is what everyone assumed. Light pushes, we just proved that. So obviously the light is shoving these little paddles and making them spin. You can watch the push of light with your own eyes right there on the shelf. What could be simpler? It is completely wrong, and the way it is wrong is gorgeous. Look closely at which way the toy spins. The black sides retreat from the light, and the shiny sides lead. Now think back to what we learned. A shiny mirror should feel more push from light than a dark surface, so if light pressure was spinning this toy, the shiny sides should be shoved backward, and the paddles should spin the other way. The toy spins the wrong direction for it to be light pressure. The evidence is right there, mocking everyone who trusts the easy answer. So what actually spins it? The bulb is not perfectly empty. A little bit of air is left inside on purpose. The black side of each paddle soaks up sunlight and gets warm. The shiny side reflects light and stays cooler. So one side of every paddle is hot and the other is cool. Now the leftover air goes to work. Air molecules bounce off the hot black side harder and faster than they bounce off the cool shiny side. Those harder bounces kick the black side backward, and around the paddles go. The toy is really being spun by warm air, not by light at all. The light only heats the paddles. The air does the shoving. Here is the beautiful twist. Lebedev, the man who first truly measured the push of light, understood this trap perfectly. It was exactly this warm air effect that he had to hunt down and banish from his own chamber. The very thing that spins the toy was the noise he spent years fighting to remove. The toy runs on his enemy, so the lesson lands hard. The most obvious demonstration of the push of light, the one everybody points to, is a fake. The real push of light is far too weak to spin that toy. The toy spins on heat and leftover air, and it even spins the wrong way to be light pressure. It fools your eyes completely. This is why science leans so hard on careful measurement instead of eyeballing. Lebedev and the Americans did not trust a spinning toy. They built vacuum chambers and hair-thin threads, precisely so they could tell the real push of light apart from the warm air pretending to be it. Their careful work settled it. Light pushes truly, but so gently that it takes a masterpiece of an experiment to catch. And that gentleness raised a burning question no one had answered yet. Everyone had measured light-shoving surfaces, but nobody had ever caught a single grain of a light in the act, striking a single tiny particle, and watched it recoil. To do that, you would need to fire light like a bullet and see something bounce. That is exactly what a man named Arthur Compton was about to do. In 1923, an American physicist is firing invisible bullets at the tiniest targets he can find. His name is Arthur Compton, and the bullets are X-rays, those savage high-energy photons that punch through skin and bone. His targets are electrons, the tiny specks of charge that swarm inside every atom. Everything measured so far had been light pushing on big surfaces, whole mirrors and whole paddles. Compton wanted to zoom all the way in and watch one grain of light hit one tiny particle, head on. If light were only a smooth wave, like Maxwell first pictured, this collision should be gentle and smeared out. The wave would wash over the electron and jiggle it softly. Nothing dramatic. Nothing like a crack of pool balls. That is where the surprise was hiding. Compton fired his X-rays into a target and watched how they bounced off the electrons inside. And the collisions did not behave like waves washing over anything. They behaved like billiard balls slamming into billiard balls. The photon struck the electron, knocked it flying off to one side, and then careened away itself in another direction, exactly the way two balls scatter on a pool table. Picture the break shot in a game of pool. The cue ball smashes into a resting ball, and both go rolling off at their own angles, the total push shared between them. That is precisely what Compton saw, except the cue ball was a grain of light and the resting ball was an electron. Light was hitting like a solid little projectile, and there was a detail that clinched it. When the photon bounced off, its colour changed. It came out a little redder than it went in, shaken a little more slowly, carrying a little less energy than before. Where did that lost energy go? Straight into the electron it had just knocked flying. The photon had spent some of its punch to shove the electron, and the books balanced perfectly. This was the smoking gun. For a wave, that colour shift made no sense at all. For a bullet, it was obvious. When a moving ball hits a resting one, the moving ball slows down and hands over some of its motion. The photon did exactly that, losing energy and reddening as it shoved the electron aside. So Compton had caught what nobody had ever seen directly: a single grain of light colliding with a single particle and behaving like a tiny solid thing with a definite push. The momentum of a photon was no longer just a number twisting a thread across a whole surface. It was a punch you could watch land, particle to particle, and the recoil proved it, and the push it delivered obeyed the exact formula we built earlier. The photon's momentum was its energy divided by the speed of light, right down the line. The theory on paper and the electrons flying off the target agreed completely. This is fully confirmed, one of the cleanest results in physics. Compton's collisions have been repeated countless times, and light always bounces like a particle carrying momentum. The world took notice fast. This single experiment did more than measure a push. It cracked open the deepest question about what light even is, and it would soon hand Compton one of the highest honours in all of science, along with a truth about photons that still unsettles people today. 4 years later, in 1927, Arthur Compton stands on a stage in Sweden, accepting the Nobel Prize. He won it for those billiard ball collisions, for catching a grain of light shoving an electron. But the prize was really for something bigger than a single clever experiment. Compton had forced the world to accept a truth about light that many brilliant people had fought against for years. Here is the truth. Light is not simply a wave. Light also comes in grains, real countable packets, and each packet carries a solid, definite push, exactly like a tiny projectile. That may sound obvious to you now because we have been calling them photons all along. Back then it was almost heresy. Maxwell had shown, beautifully, that light is a wave. Everyone loved that picture. It explained rainbows, ripples, all of it. To then claim that light also behaves like a stream of little bullets felt like a contradiction, like saying the ocean is both a smooth swell and a bucket of marbles at once. Compton's collisions ended the argument. You cannot explain his reddening, recoiling X-rays with a smooth wave. You can only explain them with grains, each carrying a fixed push. The push he measured matched the photon formula perfectly, the energy divided by the speed of light. The wave picture alone simply could not do it. Let me be clear about what his Nobel really proved, because it is subtle. It did not prove that light shoves things. Lebedev and the Americans had already nailed that. What Compton proved was how light shoves things. It shoves as grains, one packet at a time, each one carrying momentum like a solid particle, even though not one of them has any mass. So the whole story we built now has a face and a witness. The massless photon, carrying a push welded to its energy, was caught red-handed in Compton's lab, knocking electrons around like a cue ball on a break shot. And this cracked open the strangest idea in modern science. Light is somehow both things at once. It ripples like a wave when it travels, spreading and bending. It strikes like a particle when it hits, delivering a sharp packet of push. Neither picture alone is complete. Reality keeps both. That double nature is confirmed beyond any doubt. It sits at the very foundation of the physics that runs your phone, your computer, and every screen you have ever looked at. Compton's crashing photons were one of the first hard proofs of it. Here is a comparison to make the strangeness land. Imagine ocean waves rolling toward a beach, smooth and endless. Now imagine that when each wave finally hits the sand, it lands as a single hard pebble, one clean thud. That is light. It travels spread out like a wave, then arrives concentrated like a grain. Compton is the man who proved the pebble half. By now the push of light had been guessed, calculated, measured, confirmed twice, and even caught one grain at a time. You might think there was nothing left to discover. There was. Because light does not only shove things in a straight line, Under the right conditions, a beam of light can reach out, grab an object and make it spin. In 1936, a physicist hangs a small disk from a fine fibre and shines a special kind of light straight up at it, waiting to see it turn. His name is Richard Beth, working at Princeton, and he is chasing a wilder question than anyone before him. Everyone had shown that light can push in a straight line. Beth wanted to know something stranger. Can light twist? Can a beam reach out and spin an object, the way you spin a top with a flick of your fingers? To understand why he thought it might, we need one more idea about light. Light can be twisted as it travels. Some light marches straight, its waves waving flat up and down like a jump rope shaken by one person. But light can also be made to corkscrew, spiralling as it flies forward, like the stripes on a barber pole turning in place. This corkscrew light carries not just a straight push, but a spinning push, a twist. Beth's bet was bold. If corkscrew light truly carries a twist, then when it strikes an object and hands that twist over, the object should start to rotate. The beam should act like an invisible finger, spinning the disc without ever touching it. The trouble, as always, was the size of the effect. The twist a beam of light carries is even fainter than its straight push, which was already close to unmeasurable. Beth was hunting a whisper inside a whisper. He needed a setup so delicate it could feel a torque smaller than almost anything ever measured. He hung his disc from a quartz fibre finer than a spider's silk, sealed away from every draft and tremor. Then he sent his corkscrew light up through it and watched, breath held, for the tiniest rotation. The disc turned, the light twisted it, and when Beth reversed the corkscrew, spinning the light the other way, the disc turned the other way too, exactly as it should. Light had reached out and spun a real object with nothing but a twist carried in the beam. Think about what that means. A beam of light is not just a battering ram that shoves. It can also be a wrench that turns. It carries straight push and spinning push both, and it can hand either one to matter, all of it welded to energy, none of it needing any mass. Here is a way to picture the difference. A straight beam of light is like a stream of water from a hose, pushing whatever it hits. Corkscrew light is like that same stream fired at a pinwheel, setting it spinning. Same water, but now it turns things. Beth proved light has that pinwheel power too. This is confirmed, and remarkably, it is not just a curiosity anymore. Today, scientists use this exact twist of light to spin tiny objects on purpose, to build microscopic motors and to steer particles too small to see. The whisper Beth chased is now a real tool sitting in modern labs, so light can push straight and light can spin. But a puzzle has been lurking under every experiment in this whole story, and it is time to face it. Not every surface feels the same push from light. A shiny mirror and a dull black wall struck by the identical beam feel very different shoves, and the mirror, strangely, feels the stronger one. It feels exactly twice the push. Shine the same beam of light onto two walls side by side. One is a dull black surface, the other is a perfect mirror. The mirror feels twice the push, the exact same light, the exact same beam, yet the shiny wall gets shoved twice as hard as the dark one. At first that sounds backward. How can bouncing light off a surface press harder than soaking it up? The answer is one of the neatest ideas in the whole story, and you already know it from playing catch. Think about catching a baseball versus batting it back. When you catch a ball, it slams into your glove and stops dead. Your hand feels one shove, the push of stopping the ball. That is what the black wall does with light. It absorbs the photons, swallowing them completely. Each photon slams in, hands over its push, and is gone. The wall feels one shove per grain of light. Now imagine batting that ball back instead of catching it. First you have to stop it coming in, that is one shove. Then you have to fling it back out the way it came, and that takes a second shove in the same direction. Batting a ball back kicks your hand about twice as hard as simply catching it. Any kid who has caught a fastball and then tried to smack one back knows the difference in their arms. A mirror is a batter. When a photon hits a mirror, the mirror does not swallow it. It stops the photon and throws it right back the way it came. Stopping the photon is one shove. Reversing it and sending it back out is a second shove in the very same direction. So the mirror feels two shoves for every grain of light, while the black wall felt only one. Twice the push, exactly. This is not a small footnote. It is the reason engineers who want to ride on light always reach for shiny surfaces. If you are building something to be pushed by sunlight, You want a mirror, not a dark cloth, because the mirror milks twice the shove out of the same beam. Every bit of push matters when the push itself is so faint, and it goes deeper than just doubling. The mirror also feels the push in a cleaner, straighter direction, because it sends every photon bouncing back the way it came. This makes a mirror the ideal thing to place in the path of light you want to push you along. Catch a little, and you get a little. Bounce it back, and you get everything the light can give. This is fully confirmed, and it is measured precisely. A shiny reflector feels close to twice the pressure of a black absorber under the same light, right in line with the baseball logic. Physicists count on this number when they design real machines. So now we hold every piece of the core answer. A photon has no mass, yet carries a push welded to its energy. That push is a whisper on its own, crushed tiny by the vast speed of light. But it stacks, and it spins, and it doubles off a mirror. Given enough grains and enough patience, it becomes a force you can actually build with, which raises the obvious next question. If a mirror can squeeze double the push out of sunlight, could you build a giant mirror, unfurl it in space, and let the endless flood of sunlight carry a real ship across the solar system with no fuel at all? People asked exactly that, and then they built it. Picture a sailboat gliding across a calm lake, carried along by nothing but wind pressing into its cloth. For thousands of years, sailors have ridden the push of moving air. The wind is free, it never runs out. A ship with sails carries no heavy engine and burns no fuel. It simply spreads its cloth and lets the sky do the work. Now take that ancient idea and lift it off the water, all the way up into space. Out there, of course, there is no wind, no air at all. But there is something else pouring endlessly out of the sun, a flood of photons, streaming outward in every direction, each one carrying its tiny welded push. And we just learned that a mirror squeezes double the shove out of light. So here is the dream. Build an enormous feather-light mirror, unfurl it in space like a sail, and let sunlight itself push your ship along. A solar sail. The math says it can work. The sun's light presses on that sail every second, gently, without pause. On Earth, the push would be buried under wind and gravity and friction. In space, there is nothing to fight it. Each faint shove simply stacks onto the last, and the sail slowly, steadily gathers speed. Here is the beautiful part. A fueled rocket burns hard for a few minutes, then coasts forever with an empty tank. A solar sail does the opposite. It accelerates gently, but it never stops accelerating. As long as sunlight is falling on it, the push keeps coming. Day after day, month after month, that patient shove piles up. Over a long enough trip, a solar sail could outrun a rocket that started far faster, purely because it never quits. But the sail must be huge, and it must be almost impossibly thin. Sunlight is so gentle that to catch a useful push, you need a mirror spread across a vast area, thinner than a plastic grocery bag, thinner even than a soap bubble in places. Imagine a sheet of shiny film as wide as a football field, yet so light you could crumple the whole thing into your fist. That is the kind of sail this dream demands, and the payoff climbs the farther out you look. Near the sun, the light is fierce and the push is strongest. Some designs imagine diving a sail in close to our star, catching a tremendous shove while the sunlight is thick, then flinging outward faster than any fueled ship could manage. The closer to the sun, the harder the light pushes, and the faster the sail can be hurled toward the outer planets and beyond. For decades, this lived only on paper, and in the pages of science stories. Engineers sketched it, argued about it, and wondered whether such a flimsy giant sail could ever really be flown. A sheet that big and that thin might tear or tangle or refuse to open at all. Catching a whisper of sunlight to move a real machine across the real space sounded to many like a fantasy. Then a team decided to stop wondering and actually try it. They folded a shining sail into a small canister, loaded it onto a rocket, and shot it into deep space, hoping it would unfurl and catch the light. Whether it worked, and what happened when the sun's push first touched that sail millions of miles from home, is where the story turns real. In 2010, a Japanese spacecraft drifts through deep space, and a folded sail begins to unfurl from its spinning body. The mission is named Icaros, and the team back on Earth is holding its breath. Packed inside was a shining sail, folded up tight like a paper decoration. The plan was to spin the craft and let the motion fling the sail open into a wide, flat square, then wait and see if sunlight would push it. Nobody had ever truly sailed on light before. This was the first real test in the emptiness between worlds. The sail opened. It spread out into a glittering square roughly the width of a small house, its surface thinner than a human hair. And then the sunlight touched it, and the push began. Instruments on board measured the shove of the photons landing on the sail, and it matched the theory. A real spacecraft was moving through space, driven by nothing but the pressure of sunlight. The dream had left the paper. Icarus proved it could be done. It sailed toward the planet Venus, steering by tilting its sail to the light, riding the same gentle push that Kepler had guessed at and Lebedev had weighed. The first true lightship in history was flying, and it worked exactly as the physics promised. Then, in 2019, a small American spacecraft carried the idea into orbit around Earth. This one was named LightSail 2, built by a group of space enthusiasts funded by ordinary people who believed in the dream. It was tiny, about the size of a loaf of bread when folded. Once in orbit, it stretched out a shining sail as wide as a boxing ring, and it began doing something remarkable. By turning its sail toward the sun and away again, over and over, it used sunlight alone to raise its own orbit, climbing higher purely on the push of light. Think about what that means. A spacecraft with no engine, no fuel, no thruster of any kind was changing its path around the Earth, using only the shove of photons. It steered by light. It climbed by light. Every bump upward came from grains of sunlight bouncing off its mirror, each one delivering that doubled push we learned about, all of it stacking up second after second. These missions turned a century of theory into hardware. The push of light was measured in labs by Lebedev and the Americans, caught one grain at a time by Compton, and now it was flying real ships across real space. Confirmed in orbit for the whole world to track. Here is a number to hold on to. The sunlight push on one of these sails is so slight that it would take you longer to feel it than a heartbeat can measure. Yet given weeks of steady sailing, that whisper can shift a spacecraft's speed by hundreds of miles per hour. Patience turns a whisper into a highway. So the push of light can carry ships. It can lift them, steer them, and fling them between worlds. And it does all this using energy alone, with no mass anywhere in the machine that makes the shove. But the very same push that moves a spacecraft outward can be turned around and aimed inward. Aim enough light at something tiny from the right directions, and instead of speeding it up, you can freeze it almost to a dead stop. Deep in a modern laboratory, scientists are using beams of light to make atoms colder than the darkest reaches of deep space. This sounds backward. Light is warm. Sunlight heats your face. A lamp warms a room. A fire glows hot. How could shining light on something make it colder? The answer is one of the cleverest tricks in all of science, and it runs entirely on the push we have been chasing. Start with what heat really is. Temperature is just motion. In anything warm, the tiny atoms are zipping around, jittering and bouncing at wild speeds. The faster they move, the hotter it is. To make something colder, you have to slow its atoms down. To make it incredibly cold, you have to nearly stop them. Now bring in the push of light. When a photon slams into an atom, it delivers a tiny shove. The same shove Compton measured. And here is the key. If an atom is racing toward you, and you fire photons straight into its face, each photon acts like a tiny headwind, kicking against its motion and slowing it a hair. One photon barely does anything. An atom shrugs off a single grain of light, but scientists surround the atoms with laser beams coming from every direction, front, back, left, right, top and bottom. No matter which way an atom tries to dart, it runs into a stream of photons pushing back against it. Every direction it turns, the light shoves it to a crawl. Scientists call this a trap of light, and the atoms inside it slow down and down. Picture a swarm of gnats trying to fly through a room where a fine mist is blowing in from all six walls at once. Every way they turn, the mist pushes them back toward the center, until they can barely move at all. That is what the laser beams do to the atoms. They become a cage made of pure light, and the atoms inside slow, almost to a standstill. How cold does it get? These traps chill atoms to within a hair of the coldest temperature that can possibly exist, colder than anything found naturally anywhere in the universe, colder than the empty space between the stars. All of it done with light, using nothing but the gentle push of photons landing on atoms. This is fully real and fully confirmed. The scientist who worked it out won the highest prize in physics for it. Today, laser cooling runs inside some of the most precise clocks ever built, the atomic clocks that keep the time your phone uses to find its place on a map. Every time your phone shows your location, it leans on atoms held still by the push of light. Sit with how strange this is. The same shove that flings a spacecraft outward can also pin an atom in place and freeze it colder than the void. Push it one way, you launch a ship. Surround it, you build a cage of a light. The push is the same, only the arrangement changes, and once you can hold an atom still with light, a wilder idea opens up. If beams of light can trap something as tiny as an atom, could a beam grab hold of something much bigger? Could you use light to pick up, carry, and move a living thing, holding it in mid-air with nothing but a glowing beam? Under a microscope, a single living cell floats in water, held perfectly in place by an invisible beam of light. A scientist nudges a knob and the cell glides sideways, following the beam like iron filings following a magnet. She moves it wherever she wants, lifts it, sets it down, all without a single tool ever touching it. The only thing holding that cell is light. This tool has a fitting name. Optical tweezers, tweezers made of a beam. It works because of a subtle side of the push we have been studying. A tightly focused beam of light does not only shove things forward. When you squeeze a laser down to a tiny bright point, the light bends as it passes through a small clear object, and every bend hands the object a little push. Add up all those pushes, and they pull the object toward the brightest center of the beam and hold it there, trapped in the focus like a marble resting at the bottom of a bowl. So a tiny transparent thing, a plastic bead, a bacterium, a living cell, gets caught in the beam's bright heart and stays there. Move the beam, and the object comes along, because it is always tugged back toward the brightest spot. The light becomes a hand with no fingers, gentle enough to hold something alive without crushing it. Think about how delicate that is. A living cell is soft and fragile, easily torn by anything solid. Yet a beam of light can cradle it, lift it, and carry it across a droplet of water without leaving a scratch. Scientists use this to grab single bacteria, to stretch strands of the coiled instructions inside our cells, and even to reach inside a living cell and rearrange the tiny machines floating within, all with a beam. Here is a comparison to feel it. Imagine picking up a single grain of salt, but the only tool you are allowed is a flashlight. It sounds impossible. Yet that is exactly what optical tweezers do, and smaller. They routinely grab things far tinier than a grain of salt, things you could never see with your eyes, and hold them steady as a rock. This is confirmed, and it changed science. The person who invented optical tweezers won the highest prize in physics for it. Today the technique is a workhorse in biology labs around the world, letting scientists handle the machinery of life one piece at a time. Doctors and researchers studying diseases, cells, and the tiny engines inside us all reach for beams of light as their most delicate hands, and every bit of it, once again, runs on that one deep truth. The photon has no mass, yet it carries a push, and that push is real enough to hold a living thing in the air. From flinging a spacecraft across the solar system, to freezing atoms near the bottom of cold, to cradling a single cell, the same massless shove does all of it. So far, though, we have always talked about light pushing on something from the outside, a photon flying in and shoving a sail, an atom a cell. But there is a hidden version of this push that happens the other way around. Every atom that ever glowed, every flame, every star, gives itself a kick each time it releases a photon. Light does not only shove things, making light shoves you back. Somewhere in a glowing gas cloud, a single atom flickers, releases a flash of light and quietly lurches backward. We have watched light push on things from the outside all along. Now look at the flip side, the moment a photon is born. When an atom makes light, it does not get off free. The act of firing out a photon kicks the atom in the opposite direction, and this kick is one of the most important pushes in the entire universe. You already know this feeling. Stand on a skateboard and throw a heavy ball forward, and you roll backward. Fire a gun, and it kicks into your shoulder. Whenever you hurl something one way, you get shoved the other way. Scientists call this recoil, and it is a rock-solid rule. Every push has an equal push in the opposite direction. An atom emitting light obeys the same rule. When an atom releases a photon, that photon flies off carrying its little bundle of push. So the atom, to balance the books, must lurch the opposite way, exactly as hard. The atom shoves the photon out one side and the photon shoves the atom back. Making light gives the atom a tiny kick. One kick is almost nothing. An atom is unimaginably small, and a single photon's push barely stirs it. But atoms fire off photons constantly, over and over, millions upon millions of times. And here is where it gets clever. Those kicks can be aimed. Remember laser cooling from a moment ago. It runs on exactly this. An atom soaks up a photon coming from one direction, getting shoved that way, then spits a photon back out in a random direction. Because the incoming shoves all point the same way and the outgoing kicks point every which way, the pushes toward the atom win out, and the atom slows. The recoil of emitted light is the secret gear inside the whole trick. Here is a picture to hold. Imagine a person on a frozen pond, unable to walk because there is no grip. If they hold a bucket of baseballs and start hurling them one direction, each throw slides them a little the other way. Throw enough, and they glide clear across the ice. An atom firing off photons is that person, and the light is the baseballs. Every flash of light it makes nudges it along. This recoil is confirmed and measured to stunning precision. It runs the atomic clocks that time your phone, and scientists count on it every day. It is a settled, tested fact of how atoms and light behave. And now zoom out, way out. Think about a star made of an unthinkable number of atoms, all of them blazing, all of them firing off photons every instant. Each atom feels the tiny recoil kick of the light it makes, and each photon it releases goes on to shove the atoms around it. Inside a star, light is being made and absorbed and remade trillions upon trillions of times everywhere all at once. All of that pushing does not just vanish. It adds up into a force strong enough to hold up a star. The very light a star makes presses outward through its body, fighting against the crushing weight of the star's own gravity trying to collapse it. The push of light is not only a lab curiosity, it helps decide whether a star lives or dies. Deep inside the sun, a fierce war is raging every single second, and the weapon on one side is light itself. Our sun is enormous, a ball of blazing gas so wide that more than 1 million Earths could fit inside it. And all that mass has a problem. Gravity is relentlessly trying to crush it. Every ounce of the sun is pulling on every other ounce, dragging inward, squeezing toward the center. Left alone, gravity would collapse the whole sun into a tiny point. Something has to push back, hard, or the star falls in on itself. Part of what pushes back is heat, the wild motion of superhot gas straining to expand. But there is a second defender holding the sun up, and it is the star of our whole story, the push of light. In the sun's core, where the temperature is beyond imagining, nuclear fire is blazing, and it pours out a flood of photons so vast no number can hold it. Those photons stream outward, and as they climb through the sun's thick body, they slam into atom after atom, shoving each one outward as they go. This outward shove of light, spread through the entire star, presses back against gravity's inward crush. Light is holding the sun up. Picture a crowd trying to squeeze into a doorway from all sides, everyone pushing inward. Now imagine a powerful fan blowing outward through that door, strong enough to hold the crowd back. Gravity is the crowd, forever pushing in. The push of light is the fan, forever blowing out. As long as the two stay balanced, the star holds its shape, steady and alive. In a star like our sun, light does a real share of this work, though the hot gas carries most of the load. But go bigger. Look at the true giants of the sky, stars far more massive than the sun. In those monsters, the light gets so intense that its push becomes the main force holding the star up. The bigger the star, the more it leans on light to keep from collapsing. In the largest stars, the shove of photons is doing most of the fighting against gravity. Feel the strangeness of that. The lightest thing in the universe, a grain of light with no mass at all, is holding up the heaviest objects there are. A photon weighs nothing, yet a torrent of photons keeps a giant star from crushing itself into oblivion. The massless shove we have chased through labs and spacecraft is, on the grander scale, one of the things that let stars exist. This is confirmed science, worked out in careful detail and matched against the stars we watch in the sky. Astronomers rely on this balance to understand how stars are born, how they burn, and how long they live. But this sets up a dangerous question. If the push of light holds a star up, what happens when a star grows too big? What if a star becomes so massive that the light inside it pushes even harder, until the outward shove finally overpowers gravity's grip entirely? Then the very light that was holding the star together turns against it. It becomes strong enough to tear the star apart, blasting its outer layers off into space. There is a size beyond which a star simply cannot hold, because its own light will rip it to shreds. Far out in the galaxy, a monster star blazes so brightly that it is slowly tearing itself to pieces with its own light. We just saw that light holds a star up by pushing outward against gravity. For a normal star, the two forces balance and everything stays calm. But this balance has a hidden edge, a point of no return. Make a star bigger, and it burns hotter, and it pours out more light. More light means a stronger outward push, and if the star grows massive enough, that push keeps climbing until it wins. Once the push of light beats gravity, the star can no longer hold on to its own outer layers. The photons streaming out from the core slam into the star's surface gas and blow it clean off into space. Like a fire hose blasting away a pile of leaves, the star begins shedding itself, flinging its own outer skin into the dark, all because its light has grown too fierce to contain. This sets a hard ceiling on how big a star can be. There is a limit, a maximum brightness a star can reach, before its own light starts ripping it apart. Push past that limit, and the star cannot survive in one piece. Its light does the destroying. Astronomers have a name for this ceiling, and it comes from the very balance we have been describing. The push of light sets the largest size a star is allowed. This is why you never see stars beyond a certain enormous mass. Nature tries to build them, but the moment a star grows too heavy, its light turns violent and strips away the excess. The star cannot bulk up past the ceiling, because the harder it tries, the harder its own light shoves back, blasting the extra away. Light is the bouncer at the door, refusing to let any star grow too monstrous. Here is a number to feel the scale. The most massive stars known blaze millions of times brighter than our sun, and at that fury the push of their light is a storm strong enough to hurl entire oceans worth of gas off their surfaces every year. These giants are constantly bleeding themselves into space, held hostage by the ferocity of their own glow. Think about what a strange fate that is. A star's light is the thing that keeps it alive, holding it up against gravity. And that exact same light, if it grows strong enough, becomes the thing that dooms it, tearing away its body and capping how large it can ever be. The push of the massless photon giveth, and the push of the massless photon taketh away. This is confirmed, drawn from watching real giant stars shed their outer layers in exactly the way the physics predicts. Astronomers see these stars losing mass to their own radiation, right on schedule. So the push of light shapes the very stars in the sky, deciding how big they can grow and helping seal their fate. From a spinning toy on a windowsill to a spacecraft's sail, to the life and death of giant stars, this one gentle shove reaches across every scale there is. But we have been quietly assuming something this whole time, and it is time to question it. We keep saying light has no mass. Yet light clearly carries energy and push, and energy and mass are deeply linked. So here is a puzzle that will bend your mind. If you trap a bunch of light inside a box, does the box get heavier? Imagine a perfect box with mirrored walls on the inside, and you fill it with nothing but trapped light, bouncing back and forth forever. The box itself is empty of any solid stuff. No gas, no dust, no matter of any kind. Just photons racing between the mirrors, bouncing endlessly, never escaping. Now weigh the box. Here is the mind-bending truth. That box weighs more full of light than it did empty. The trapped glow makes the box heavier. Stop and feel how impossible that sounds. We have said, again and again, that light has no mass. A photon weighs nothing. Yet a box crammed with weightless photons weighs more than the same box empty. How can a pile of nothing add weight? The answer reaches back to Einstein's most famous idea, the one on all the posters. Energy and mass are two forms of the same thing. Energy has weight. Anything holding extra energy is, in a real and measurable way, heavier for it. And light is pure energy. So a box full of light holds extra energy, and that energy shows up as extra weight on the scale. Here is the subtle key that untangles it. A single photon flying free has no mass. That is true. But mass is really about energy that stays put in one place. A lone photon never stays put. It flies off at the speed of light and is gone. Trap that photon in a mirrored box though, and force it to bounce back and forth, and now its energy is stuck in one spot. Energy pinned in place behaves exactly like mass. The trapped light gives the box weight. Picture a swarm of bees. One bee flying off across a field weighs almost nothing to you, but seal a whole swarm inside a jar, and now you're holding all their weight in your hand, buzzing and bouncing but trapped. The photons in the box are like that swarm. Free. They carry their energy away. Caged. Their energy sits with you, and it weighs something. So the box of light is heavier, and by a real amount you could measure with a good enough scale. This is fully confirmed by the deepest tested rules in physics. It is not a trick of words. The energy of the trapped light genuinely adds to the weight of the box. And this cracks open something huge about the whole story. We kept treating mass and energy as separate ideas, one giving weight and one giving push. They were never truly separate. A massless photon can lend its energy to a box, and that energy becomes weight. The line between the weightless and the weighty is far blurrier than it first seemed, which forces a deeper question, maybe the deepest in this whole journey. We know that mass creates gravity. Heavy things pull on other things. The Earth pulls you down, the Sun holds the planets, mass reaches out and tugs. But if energy can act like mass, and light is pure energy, then here is the staggering possibility. Does light itself have gravity? Does a beam of light carrying no mass at all still reach out and pull on the world around it, the way a planet does? The answer changes what gravity even means. Here is a truth that overturns what most people believe about gravity. Mass is not what makes gravity. Energy is. We grow up thinking heavy things make gravity. The Earth is massive, so it pulls us down. The Sun is massive, so it holds the planets. Mass pulls, we assume, and that is that. This picture is close, and for most everyday things it works fine, but it is missing the deeper truth that Einstein uncovered, and that truth is stranger and grander. What actually creates gravity is energy. Every form of energy. Mass is one kind of energy, the kind locked inside solid stuff, so mass does make gravity. But it is only one entry on a longer list. Heat is energy, so heat makes gravity. Motion is energy, so motion makes gravity. And light is energy, pure and simple, so light makes gravity too. Read that again slowly. A beam of light, carrying no mass whatsoever, still bends the world around it with a pull of its own. The photon that weighs nothing still reaches out and tugs, because it carries energy, and energy is the true source of gravity. The massless thing gravitates. The pull from light is staggeringly weak, far too faint to ever notice in a flashlight beam or a sunbeam. But it is real. If you could gather a truly ferocious amount of light into one place, its energy would warp the space around it and pull on nearby things, exactly the way a lump of matter would. In fact, physicists can imagine a star made purely of light, held together by the gravity of its own glow. Light pulling on light, with no matter anywhere in it. This flips our whole story on its head one final time. We started asking how something with no mass could carry a push. We have now arrived somewhere far deeper. Something with no mass can also have gravity. The photon shoves things and the photon pulls things, and it does both while weighing absolutely nothing. Mass was never the star of the show. Energy was, the entire time. Here is a way to hold it. Think of gravity as a tax that every kind of energy has to pay. Solid matter pays it, heat pays it, motion pays it, and light pays it too. Nothing carrying energy gets to skip the tax. Because light carries energy, light gravitates, right along with everything else in the universe. This is confirmed sitting at the heart of Einstein's greatest theory, the one that describes gravity itself. It has passed every test thrown at it for over 100 years. Energy makes gravity, and light is energy, so light makes gravity. Settled, tested, real. And this idea has a famous flip side that was actually caught in the act. If energy makes gravity, and gravity is really a warping of space, then gravity should reach out and grab light right back. A massive object should bend the path of a passing beam, tugging the light off its straight line as it flies by. In 1919, during a total eclipse of the sun, a team of scientists set out to catch exactly this. They aimed to watch the light of distant stars bend as it skimmed past our sun, to see with their own instruments whether gravity truly pulls on light. What they found made Einstein famous overnight. On a remote island in 1919, a British astronomer waits for the moon to swallow the sun, hoping to catch starlight bending in the dark. His name is Arthur Eddington, and he is testing the wildest prediction anyone had made about gravity and light. Einstein had claimed that gravity bends the path of light. A massive object like the sun, he said, should tug on any light passing close by, curving the beam ever so slightly off its straight line. If true, it would prove that gravity and light are locked together in a deep new way. The problem was seeing it. Starlight grazing the edge of the sun would be bent, yes, but the sun is blindingly bright, and you can never see faint stars sitting right beside it. The sun's glare washes them out completely. To catch the bending, Eddington needed the sun covered up, its face blocked while the stars beside it stayed visible. He needed a total eclipse. So when the moon slid perfectly in front of the sun that year, plunging the day into darkness, Eddington was ready with his cameras. For a few precious minutes, the sun's blazing face was hidden, and the stars near its edge popped into view. He photographed them carefully. Then he compared their positions to where those same stars sat when the sun was nowhere near them. The stars had moved. The ones whose light skimmed past the sun appeared shoved slightly out of place, exactly as if their light had been bent as it flew by the sun's gravity. And the amount of bending matched Einstein's prediction. Gravity really does grab light and curve its path. The beam that weighs nothing still gets pulled. This was the other half of the truth from the last chapter. Light makes gravity because light carries energy, and gravity in turn bends light, because gravity warps the very space that light travels through. The two are bound together, pulling and bending each other, with the massless photon caught right in the middle of it all. Picture a straight road running across a stretched rubber sheet. Set a heavy ball on the sheet and it sags, and the road bends around the dip. Anything travelling that road, even a beam of light, has to follow the curve. The sun makes exactly that kind of dip in space, and the starlight, obeying the bend, arrives looking shifted. Eddington photographed the bend. When the results were announced, Einstein became world famous overnight. Newspapers across the globe ran the story. A quiet prediction about weightless light being tugged by gravity had been caught in a photograph, and it changed how humanity understood the universe. This is confirmed, tested countless times since, and rock solid. So the photon, massless as ever, both makes gravity and answers to it. It shoves things, it spins things, it pulls things, and it gets pulled. All without a speck of mass anywhere. By now you might wonder if the photon is alone in this strangeness, the one weird, massless thing in a universe of heavy stuff. It turns out the photon has company. There are other massless things woven into the fabric of reality, some already found, one still hunted, and these massless cousins run some of the most important forces in existence. The photon is not the only weightless thing racing through the universe. It has relatives, and they run forces you depend on every second. We have spent this whole journey with the photon, the grain of light, massless yet full of push. Now meet its family. Nature turns out to build several of its most important messengers with no mass at all, and each one, like the photon, must fly at the speed of light and can never rest. The photon is simply the one we can see. The first cousin is called the gluon, and it does one of the most vital jobs in existence. Deep inside every atom sits a tiny core, and inside that core are even tinier building blocks that must be glued together with tremendous strength. The gluon is the glue. It carries the powerful force that binds the heart of every atom, holding together the very stuff you and everything around you are made of. And the gluon, like the photon, has no mass. Sit with that. The force holding together the center of every atom in your body is carried by a weightless messenger, flying at light speed, never resting. Without the massless gluon doing its job, atoms would fall apart and nothing solid could exist. A thing with no mass holds all matter together. This is confirmed, a bedrock piece of the physics that describes the tiny world. Then there is a cousin that scientists strongly believe in but have never yet caught. Its name is the graviton, and if it exists, it carries the force of gravity itself. Every idea we have about how gravity might work at the tiniest scale suggests that gravity should be carried by a messenger, a grain of gravity, the way light comes in grains. And that grain, the graviton, should be massless, flying at the speed of light like its cousins. Here is the honest truth signal. The gluon is confirmed, found, and studied every day. The graviton is still a theory, a strongly expected messenger that has never been directly detected. Gravity is so fantastically weak that catching a single grain of it may be beyond any machine we can build. So the graviton sits in the space between prediction and proof, waiting. Picture a family of runners, all of them born unable to slow down, all sprinting at the one speed nature allows. The photon runs, carrying light, and the force between charged things. The gluon runs, carrying the force that binds every atom's heart. And the graviton, if it is out there, runs too, carrying gravity across the cosmos. A whole family of weightless sprinters, each one holding the universe together in its own way. What ties them all together is the exact rule we uncovered at the start. Anything with no mass must fly at the speed of light, carrying energy and push welded together, never able to stop. The photon showed us the rule. Its massless cousins obey it too. Being weightless is not a strange exception. It is a whole category of things, running some of the deepest machinery of reality. So the massless photon is part of a grand family, and its push is one thread in a much larger weave. Which brings us back at last toward the biggest dream this push has ever inspired. If a gentle shove of light can sail a ship across our solar system, could a truly ferocious blast of light fling something all the way to another star? A team of scientists and dreamers stands before an idea so bold it sounds impossible. Build the most powerful light beam ever made and use it to fire a spacecraft to another star. The project is called Breakthrough Starshot, and here is the dream at its heart. The nearest star beyond our sun is staggeringly far away, so distant that a normal rocket would take tens of thousands of years to crawl there. No fuel tank could ever hold enough to make the trip in a human lifetime. So the plan throws out the rocket entirely and reaches once more for the push of light. The idea works like this. Build a tiny spacecraft, smaller than your hand, weighing almost nothing, with a shining sail attached like a microscopic version of the solar sails we met earlier. Then, back on Earth, build an enormous array of lasers, thousands of them working together aimed at the sail. Fire that colossal beam at the little sail and hold it there. The push of all that light slams into the sail and shoves the tiny ship forward, faster and faster. Because the ship is so light and the laser so powerful, the push can accelerate it to a speed no spacecraft has ever come close to. The plan aims to fling the little probe up to a fifth of the speed of light. At that blistering pace, the journey to the nearest star would take about 20 years instead of tens of thousands. A trip that once meant 1,000 human lifetimes could shrink to a single one. Feel the leap here? The solar sails we saw earlier drifted gently, nudged by soft sunlight over weeks. Starshot cranks that same idea to its absolute limit, replacing gentle sunlight with a laser so intense it does in minutes what sunlight would take years to do. Same physics, same massless push, dialed up to a violence that could hurl a chip between the stars. Here is the scale of it. The laser array this plan imagines would, for a few minutes, pour out more power than entire cities use, all focused onto a sail smaller than a kite. That savage flood of photons, each carrying its tiny welded push, would stack into a shove strong enough to punch a spacecraft to a fifth of light speed in the blink of a few minutes. Now, the honest truth signal. Starshot is not built. It is a real, funded project with real scientists working on it, but it remains a dream on the drawing board, wrestling with enormous challenges. Building a laser that powerful, a sail that can survive the blast, and a chip that can phone home across the stars are all problems still unsolved. This is a serious plan, not yet a reality. But the physics underneath it is completely sound. The same physics Lebedev measured and Icaros flew. The push of light is real. It stacks, and in principle it can carry a ship to another star. What stands in the way is engineering, not doubt about whether light can push. So the humble shove of the massless photon, too faint to feel on your skin, might one day be the very thing that carries humanity's first messenger to another sun. From a whisper on a windmill toy to a bridge between the stars, hold two facts side by side and marvel at how far apart they sit. The push from a single photon is almost nothing, yet that push helps shape entire galaxies. We have chased this shove across an enormous range. On the small end, one photon delivers a push so faint it beggars belief. To feel the shove of a single grain of a light, you would have to be more sensitive than any living thing has ever been. It is a whisper beneath a whisper beneath a whisper, gone before it arrives, and yet look at everything that same push accomplishes. It steers real spacecraft flying between the planets right now, engineers adjusting their paths using the gentle pressure of sunlight. It sailed Icaros toward Venus and lifted Lightsail 2 higher into orbit. It holds up stars against their own crushing gravity. It sets the largest size a star can ever grow. The tiniest push in nature runs some of the biggest machinery in the cosmos. How can both be true? The answer is the same lesson we keep meeting, and it never stops being beautiful. Numbers and time. The push of one photon is nothing, but the universe deals in photons beyond all counting, poured out over spans of time beyond all imagining. Stack an unthinkable number of tiny shoves over an unthinkable stretch of time, and the whisper becomes a roar. Go to the grandest scale of all, and the push of light helps sculpt galaxies. When new stars ignite in a giant cloud of gas, their fierce light pushes on the surrounding gas, blowing it outward, carving bubbles and shaping where the next stars can form. The shove of starlight helps decide how a galaxy grows, where its stars are born, and how its gas is arranged. The push we started measuring on a hair-thin thread reaches all the way up to the architecture of galaxies. Here is a comparison to feel the span. Think of a single grain of sand. Alone, it is nothing, too light to matter. But grains of sand, in vast enough numbers over vast enough time, build entire deserts and pile into dunes taller than buildings. The push of one photon is that single grain. The flood of starlight across a galaxy is the desert. Same tiny unit, unimaginable total. This is confirmed at every scale scientists can check. In the lab, they measure the single tiny shove. In space, they watch spacecraft ride it. In the sky, they see starlight carving gas clouds exactly as the physics predicts. The push of light is real from the smallest grain to the largest galaxy, and it all obeys that one formula we built, energy divided by the speed of light. So the massless photon, weighing nothing, carrying a push too faint to feel, turns out to be one of the great shapers of reality. It moves ships, holds up stars, caps their size, and helps mold the galaxies themselves. All from a shove that starts as almost nothing. But this raises a question that is closer to home, and maybe you've been wondering it this whole time. Every second, sunlight is falling on your skin, each photon delivering its tiny push. So why can you not feel it? And is there any way, any situation at all, where a human being could actually sense the pressure of light pressing against their body? Right now, sunlight is pressing on your skin, shoving you gently, and you feel absolutely none of it. Every photon landing on you delivers its push, the same push that sails spacecraft and holds up stars. Trillions of them are striking your body this very moment, and yet you sense nothing at all. So the question is simple and fair. Why can you not feel the push of light? And could you ever? We already know the reason it is so weak. The push of a photon is its energy split across the speed of light, and that speed is so gigantic that the shove gets crushed down to a whisper. Let me make it concrete for your own body. The total push of full sunlight on a person standing in the open is smaller than the weight of a single grain of rice resting on your shoulder. You cannot feel a grain of rice landing softly, and you cannot feel sunlight's push either. It is drowned out by every breath, every heartbeat, every stir of the air. So in ordinary life, feeling the push of light is hopeless. It is simply too gentle, buried under noise 1,000 times louder. No human has ever felt sunlight shove them, and no human ever will under a normal sky. But push the situation to an extreme, and things change. The push of a light grows with the intensity of the light. Make the light fierce enough, and the shove climbs from a whisper toward something real. This is exactly why the strongest lasers ever built can deliver a genuine mechanical push, strong enough to dent metal or drive tiny objects. Crank the light high enough, and its push stops being a whisper. Could a human ever feel it? In principle, if you stood in a beam intense enough to shove you noticeably, the honest answer is grim. Light that fierce would burn and blind you long before you felt any push against your body. The energy would cook your skin while the shove was still too faint to notice, so you could never safely feel the pressure of light. By the time the push was strong enough to sense, the light would already be destroying you. Here is a way to hold the strangeness. Imagine a force that is touching every inch of your body all day, every day of your life, that you are completely unable to feel. That is the push of sunlight. It is on you constantly, real and measurable, and forever below the floor of what your senses can catch. You live inside a gentle, endless shove you will never notice. This is fully confirmed. Scientists know precisely how hard sunlight pushes on a human body, and it is far, far too weak to feel. The only way to make light's push noticeable is to make the light so intense it becomes deadly. Your inability to feel sunlight's shove is not a mystery. It is a promise the numbers make. So we have traced the push of light from a comet's tail to a galaxy's shape, from a spinning toy to a bridge between stars, and even onto your own unfeeling skin. But underneath all of it, one deep question has been quietly waiting. We keep saying light carries momentum without mass. What if this strangeness is not really about light at all? What if momentum was never truly about mass in the first place? Here is the twist that reframes everything we have learned. Momentum without mass is not a special quirk of light. It is a property of something deeper, and light is only one example. All journey long, we treated the photon as the strange one, the oddball that carries a push while weighing nothing. But step back, and a bigger picture appears. The real carrier of this push is not the photon itself. It is the field the photon lives in. And to understand that, we need one new idea, gently. Physicists have learned that the whole universe is filled with invisible fields, stretching through all of space. There is an electric and magnetic field spread everywhere, and light is a ripple travelling through it, the way a wave is a ripple travelling through the ocean. The photon is a grain of that ripple, and here is the key. The field itself, this invisible ocean filling all of space, can hold energy and can hold momentum, all on its own. So the push of light was never really riding inside a tiny massless ball. It was living in the field, in the invisible ocean, and the photon was just the ripple carrying it. Momentum, it turns out, is something a field can hold and pass along, whether or not any mass is anywhere nearby. The field is the true owner of the push. This dissolves the original puzzle at its root. We kept asking how a massless thing could carry momentum, as if momentum belonged to mass and light was cheating. The deeper truth is that momentum belongs to fields. Mass is just one way to store it. A moving baseball stores momentum in its mass. A beam of light stores momentum in its field. Both are real. Neither is more fundamental than the other. The field version was there all along, waiting under the surface. Picture the ocean again. A wave rolling across the sea carries real energy and a real push, enough to knock you flat, and there is no solid object riding along inside the wave. The push belongs to the water itself, moving as a wave. Light is like that. The push belongs to the field, moving as a wave. The photon is the crest, but the ocean carries the force. This is confirmed, and it sits at the foundation of modern physics. The idea that fields fill all of space and carry energy and momentum is one of the most tested, most trusted ideas science has ever built. Everything from your phone to the deepest experiments runs on it. Momentum lives in fields, so the massless photon was never breaking a rule. It was showing us a rule we had missed. Momentum was never truly chained to mass. It was always a thing that fields can carry, and mass was only the most familiar case, not the whole story. But there is one more layer beneath even this, the deepest bedrock of all. We have explained where momentum lives. We have not yet asked why momentum exists at all, why the universe bothers to conserve it, why the push can never simply vanish. And the answer to that final question is the most beautiful idea in all of physics. It says momentum flows from the plainest fact about space itself, a fact so simple you have never once thought to question it. Here is the deepest answer of all, and it comes from one of the most beautiful ideas any human being ever had. Momentum exists because space is the same everywhere. We have journeyed a long way. We watched a comet's tail point the wrong direction, weighed the push of light on a thread, caught a photon shoving an electron, sailed real ships on sunlight, and found the push living inside invisible fields. But under every step lay one unspoken fact. Momentum is conserved. The push never simply disappears. When one thing loses it, another gains it. Always. Everywhere. Why? Why does the universe guard momentum so fiercely? The answer came from a mathematician named Emmy Noether, and it is breathtaking. She proved that every deep law of conservation in physics comes from a symmetry, a sameness in nature, and the conservation of momentum comes from one particular sameness. The laws of physics are the same in every place. Move your experiment 10 feet to the left or 1,000,000 miles into space, and the rules do not change. Space treats every location alike. That simple fact, that space is the same from spot to spot, is the reason momentum exists and is conserved. Read that again, because it is astonishing. The push a comet's tail feels, the shove that sails a spacecraft, the recoil of a glowing atom, all of it flows from the plain truth that space plays fair, offering the same laws in every location. And notice what is gloriously absent from that reason. There is no mention of mass, none. Momentum comes from the evenness of space itself, and space does not care whether a thing is heavy or weightless. So of course a massless photon carries momentum. Momentum was never about mass to begin with. It was about the deepest symmetry of the universe, a symmetry that applies to light exactly as much as to a bowling ball. The whole mystery we started with now melts completely away. We asked how a photon could carry a push without any mass. We were trapped by the schoolyard rule, weight times speed, thinking mass was the source of the push. It never was. The true source is the sameness of space, and light obeys that source just like everything else. The photon was never breaking a law. It was showing us the real law, hidden beneath the simple one we learned as children. Picture space as an endless, perfectly level field, identical in every direction, no hill favouring one spot over another. On a field that fair, anything set rolling keeps its push, because nothing about one location differs from the next to steal it away. That flawless evenness is why momentum endures, and a photon rolling across that same fair field keeps its push for the same reason a planet does. This is confirmed, one of the most profound and tested truths in all of science. Noether's insight underpins the deepest physics we know, and it has never once failed. Momentum flows from the symmetry of space, for light and matter alike. So the answer to our question, the push without mass, was hiding in plain sight the entire time. Light carries momentum because momentum was never the property of mass. It belongs to energy, to fields, and in the end to the simple, staggering fact that space itself is the same everywhere you go. The weightless photon has been obeying that truth since the first instant of the universe, and it will go on obeying it, at the speed of light, forever.